Okay, so the title of my presentation today is Social Learning and Inverse Reinforcement Learning. This talk is from a statistical signal processing perspective, which is my background, and also includes some fairly interesting ideas from microeconomics, which is something I've been quite interested in during the past few years. So if you think about the big picture ideas, in very simple terms, statistical signal processing is estimation-centric. That is, if you're given noisy observations of a signal, your aim is to reconstruct the signal in whatever way, in a Bayesian or non-Bayesian fashion, or whatever. It boils down to reconstructing signals given probabilistic descriptions of noise. If you look at a more higher level of behavioral economics, that is decision-centric. So behavioral economics deals with how can you construct clever generative models for how humans make decisions given noisy measurements. And the third ingredient in this mix is how do you interface a human decision maker with a statistical signal processing algorithm? Inverse reinforcement learning is one ingredient in there because that says the following. If you were to look at the decisions of an expert, a human, for example, can you figure out what is the utility function the expert is optimizing in order to make the decisions? Now, this is a fairly simplistic description. We'll give you something more sophisticated later. So you can view it almost as system identification at a decision-making level. So the motivation for these three ingredients is really the human sensor interface, where you have state-of-the-art statistical signal processing, which is pretty much done. I mean, there are incremental improvements, but statistical signal processing in its sense is pretty much done. There's sophisticated techniques. Behavioral economics, there's still a lot to be done because understanding how humans make decisions is very hard. Combining the two and trying to interface them so that you have a mathematical theory which allows you to design engineering systems where you can say how a human absorbs information from sensors, how humans make decisions, how those decisions can affect the future of a sensor and so on, are problems of significant interest. And this talk is going to look at some of those aspects, but in a very simplistic way, given the time constraints of 1 hour. So this talk actually has two parts. The first part deals with something called social learning models and sequential detection. So in simple terms, part one of the talk deals with, in a really simplistic way, multiple humans who are interacting and making decisions sequentially. So it's a very stylized system, not super real, but it's a very simplistic version of the story. And there is a statistical signal processing algorithm like a change detector. And how do you interface the two? And even in this simplistic setup, some really weird stuff happens, as we'll show you, some really interesting stuff. So we'll first mention something called Bayesian social learning, which is a very simple model of how humans sequentially make decisions. And then we'll discuss what quickest change detection is, and then we'll put the two together. And the outcome of part one is that even a simple behavioral economics model, the detection theory can yield pretty weird behavior as we'll see. Then part two of the talk will deal with the inverse problem. So we're looking at decisions from a decision maker, and what inverse reinforcement learning deals with is how do I estimate the utility function of the decision maker? Okay. So in simple terms, we answer two questions. The first question is, are the decisions consistent with constrained utility maximization? And if so, how do you estimate the utility function? Okay. So now IRL itself, so IRL is the acronym for inverse reinforcement learning. It's quite a large area, and the techniques we're going to use actually are from microeconomics called reveal preferences, and they give us surprisingly general ways of addressing IRL as we'll discuss in part two of the talk. So those are the two parts of the talk. I'm going to go on to part one now, which first discusses the basic social learning protocol in a Bayesian context, which is very, very simplistic, but even in that simple setup, interesting stuff happens. Okay, so let's directly jump into it, the Bayesian social learning protocol. So if you go back to, I guess, elementary probability, what one learns in high school or first year university, we can think of the classical Bayesian estimation problem. We have a random variable x, and for extreme simplicity here, we're assuming that x belongs to one of a finite number of values, 1 to cap x, and there is some prior pi 0. Okay, so this is a prior probability mass function. And classical Bayes rule operates like so. If I have a belief, which is a probability mass function of x, given observations from y1 to yk minus 1, and then I obtain an additional observation yk with the likelihood p of y given x, then just elementary Bayes rule tells you that your posterior is simply the prior times the likelihood divided by a normalization factor, so it's simply proportional. Okay, that's Bayes rule. That's simply elementary high school probability. We want to write this in a slightly different way so as to introduce social learning, and the slightly different way we're going to write this is that we're going to interpret K here as an agent. So you have a bunch of agents acting sequentially over time. So agent K observes the observation yk, and then updates the belief of x, like so, where this was the belief at agent K minus 1. So right now it's simply Bayes rule, but it's useful to keep this diagram in mind because in this diagram, we have essentially agent 1, which takes observation 1, shares its belief with agent 2, which takes observation 2, and so on. And this is classical Bayes rule, really simplistic stuff. Okay, now let's kind of slightly tweak this model and go on to the social learning protocol. So it's almost the same as before. Again, we have a random variable x, which takes on one of finite number of values with a prior pi 0. Now the difference is that our prior is the conditional probability of x given the decisions of the previous agents. So we need to figure out how these decisions are made and how do we do a recursion over k. So the decisions are made as follows. So just like classical Bayes rule, agent k has an observation yk, the likelihood. And of course, this observation set is finite. We're assuming that. And then what agent k does, it chooses a decision a of k to minimize a cost function c of xa. Now, you don't know x because x is observed in noise. So the best the agent can do is minimize the conditional expectation of the cost of x comma a, and given all the information it has. So we're assuming it's a completely rational agent. And all the information the agent has is, of course, its private observation yk, which it observed, and the belief which was available before it took the observation. So this is what the agent optimizes and chooses the action AK, which is really easy to do. Now, what happens then is, of course, we need to construct a recursion to update the public belief as to what happens at time k for the entire system. So that's again Bayesian. The public belief is the prior times the likelihood. Now, this likelihood is somewhat more complex because the likelihood is based on observing the decision of the agent, no longer an observation. I'm looking at the decision. But of course, this decision is a function of the observation, so you can unravel what the observation was. And if you write it down, you will see that it becomes something of this form here. This is the likelihood, that's the prior. So this is also Bayes rule, but there's something quite stunningly interesting in this Bayes rule. In classical Bayes rule, the prior and the likelihood are two completely different parameters. In the social learning protocol, notice that this is the prior, but the likelihood is a function of the prior. The prior enters the likelihood. Why? Because the action depends on the prior, and you're only observing the action. So now you have a weird form of Bayes rule where essentially the likelihood is a discontinuous function, discontinuous because there's an argument. It's a funny, nasty function of the prior, and you have a prior. And because of this, funny stuff happens. Okay, even with this really simplistic setup, some fairly interesting stuff happens. And one of the major results in this, which has been proved by many people, but I guess one of the major references was in 1992. Actually, a version of this was proved in information theory by Culver and Hellman in the 1970s. This is a pretty interesting result, and it tells you the following. So you can actually code this up in MATLAB pretty easily. It's about 3 or 4 lines. And you'll observe something interesting happening. After a while, all agents will pick exactly the same decision, regardless of their observations. So they form a herd. They lose the rationality of looking at the observation-making decision. They simply parrot the decision of the previous agent. And you can actually state that formally. The agents eventually choose the same action for a finite k with probability 1. And remember, if I choose the same action as the previous guy, then the social learning stops because my action contains no information about my observation. Each time I take an action, it contains my observation, but if my action is completely independent of my observation, I become somewhat irrational, then social learning stops. In a sense, the update of pi k freezes. And you can actually prove that fairly straightforwardly. So it's an elementary proof using the martingale convergence theorem. So in simple terms, the martingale convergence theorem will tell you that after a finite amount of time, because your observations are finite, this term here will become independent of yk. Okay, assume that's the case. So this guy goes outside the summation. The summation of yk just becomes 1. So what you have is the prior is equal to the posterior. Okay, so you freeze. Essentially, your Bayesian learning stops. And that's what happens, and this is generic in any system where you have this kind of finite actions. So this explains a lot of issues. I mean, people look at things like why, if you're walking down the street and there are 2 restaurants, one restaurant is full of people, one restaurant is empty, people end up only going to the restaurant which is full and the empty restaurant remains empty. That's a form of herding. There's many types of herding that way, and that's kind of a pretty standard setup. So that's classical herding. It's a phenomenon which can be generalized actually to other cases. So it's been generalized even to more general graphs. Here I've considered a linear network, agent 1, agent 2, agent 3, but this can be generalized to arbitrary networks. Herding is a feature of most decision makers when you have finite observations and you make finite decisions. And it's an issue. Okay, so there are many problems one can pose as to how do you model herding, how do you delay herding, and so on. Rather than do that due to a lack of time, what I want to talk about now, because we're talking about how humans relate to signal processing, I want to talk about how that social learning protocol fits in with one of the simplest type of stochastic decision-making problems, which is quickest change detection. So roughly what we've spoken about so far was a sensor, which takes P of y given x in social learning, a Bayesian estimator, which updates the belief, and optimize the local utility. So social learning is really these 3 ingredients as well. What we're going to do now is close the loop. We're going to add a controller which controls how the system works. So you can view this controller as a global decision maker deciding how this local individual makes decisions. So you're looking at an interaction between 2 decision makers. A global decision maker trying to detect if there's a change or no change, and a local decision maker making the local decisions. So in simple terms, the question is this: I am looking at decisions of individual humans doing social learning. By looking at the decisions, I want to detect, was there a change in my underlying state of nature? It's as simple as that. That's the change detection problem. I mentioned here Daniel Kahneman because this idea of having 2 decision makers kind of fits into this idea of thinking fast and slow. Humans, when they make decisions, work on 2 time scales. They make fast, impulsive decisions, and then they make slower, more strategic decisions. And in a sense, this very simplistic diagram takes that into account. It also can be viewed as how local and global decision makers interact. Okay, so let's look at the problem. So what is classical quickest change detection? This is a well-studied problem since the 1950s, and it's the following problem. I have a bunch of observations, assume they're independent over time, until time tau 0, which is unknown to the decision maker. The observations are from a distribution B1. After time tau 0, they're from a distribution B2, and the detector or the decision maker wishes to estimate the time tau 0, which is change time. This is a Bayesian setup, so we have to give a probability description for tau 0, assume it's geometrically distributed. That's simply a Bayesian setup. Okay, so this is the classical quickest change detection. It's a quickest change detection problem because I'm trying to estimate tau 0 to optimize a quickest change criteria, which is called actually the Kolmogorov condition for disorder. And that condition I'm trying to choose is to minimize the following cost. So my detector is doing this. This is classical quickest change detection. Let's explain what this is. So the detector announces a change at time tau. Okay, this is what the detector estimates as tau 0, and it pays a penalty. If tau is substantially bigger than tau 0, I pay a delay penalty. Okay, so this is tau minus tau 0. The plus means it's either 0 or greater than 0. So every time tau exceeds tau 0, I pay a delay penalty. Meaning that I can wait for a very long time, make a very good decision, but then I pay a huge delay penalty. Or I can act very quickly, also make the wrong decision. If I decide the system has changed before it's changed, I pay a false alarm penalty. So this is a classical quickest change detection. Trade-off between false alarm, which is acting too quickly, or delay penalty, acting too slowly. And it's been known since the 1950s, it's an elementary proof using stochastic dynamic programming, that your optimal policy has the following structure. So the horizontal axis here is your probability of change given your observations, computed using Bayes rule, classical Bayes rule. And that probability, whoops, that was not meant to happen. I don't know what I did there, but okay, but this, whatever I did, this is back to what we have, so that's okay. Okay, so we're here. So what we do here is we compute the probability of change given my observations using exactly the kind of Bayesian update I told you in Bayes rule. And if that probability of change exceeds a particular threshold, I'm not sure what I did there, but maybe that's all I need to do. Also, that's yeah. Okay, that's fascinating text. It still is visible. So maybe I just put that. Okay, so as long as that probability of change exceeds, it's less than a threshold, then I declare there's no change. It makes sense. If the probability of change is less than some value, then I say there's no change. The moment that probability of change using Bayes rule exceeds a value, then I say there's a change, and we declare it. That's classical quickest detection. Very straightforward. So now let's go down to the more sophisticated setup where we do exactly the same hookup as classical quickest detection, but we now change our setup so that the agents are performing social learning. So rather than looking at pi k being the probability of change given my observations, I'll now look at pi k as the probability of change given the decisions of the previous decision makers, as I did in classical detection. So the protocol is exactly the same as I had in the previous page. I have a decision maker who makes observations, optimizes a local utility to make those decisions, and then updates the belief. And the global decision maker is looking at these decisions of the local decision maker. Maybe the first guy chose a 1, sent its decision to the second guy chose a 2, maybe the third guy chose a 2, then a 1, or whatever, it doesn't matter. And by using these decisions, the global decision maker is trying to infer, has the underlying state changed? So it's simply a social learning version of the classical problem. What's changed now is that the belief update, the Bayes rule, is changed by a social learning protocol. Well, what happens here is something quite stunning. And in the classical quickest detection, remember I told you optimal policy was a threshold like this. Now what happens is you have a multi-threshold behavior, which is very counterintuitive. So again, the horizontal axis is the posterior probability of change. The vertical axis is the action you take to declare if change has happened or not. And notice what happens here, that as the probability of change becomes larger, then you say there's a change. It makes sense. It exceeds a particular value, you say there's a change. But as the probability of change becomes even larger, it's optimal to declare there's no change. And that's extremely counterintuitive. And so what you have is this multi-threshold type policy, which is typically never true in detection problems or in any stopping time problem. In simple terms, what happens is that the stopping set in classical problems is a convex set because it's connected. Now it's a non-convex set because it's of course disconnected. And you almost never have non-convexity of stopping sets in classical decision problems, which you do have here when you introduce this social learning protocol. So the main result, at least in the simple sense, is that the optimal policy is a multi-threshold. The stopping state is non-convex. What this means is that if you're trying to make global decisions as to whether a system has changed or not, by looking at local decisions, the problem is quite hard. It's not a simple threshold policy, it's much more complex. At a more sophisticated level, it means that if you have a bureaucracy of where you have workers who are kind of making individual recommendations, and you have a higher level entity, the manager, who's using those recommendations to decide if a system has changed, it's a non-trivial problem. Deciding when the system has changed has these highly irregular optimal policies, which make it actually pretty hard to solve. Actually, these kinds of problems have been looked at in other ways in an area called team decision theory, and John Tsitsiklis in the 1980s had some results quite similar to this, but not in this vein. Okay, so what I want to talk about next is a little bit is why do you have this kind of unusual behavior? So this is slightly more technical, but it's probably worthwhile at least briefly stating why that's the case. So the question is, why is it you have this multi-threshold behavior, which is very unusual, even for a simple stopping time problem? And it really has to do with the same idea I mentioned before in social learning, where the likelihood is a nonlinear function of the prior. Remember I told you the funny business in social learning is the Bayesian update is weird, but the likelihood depends on the prior. So if you think about this idea of quickest change detection, your posterior update is a function of the prior and the decision made, because this is what social learning is. This is the likelihood. This is a transition probability, which tells you how likely you are to change. And it's this term here which really screws up stuff. So in a classical Bayesian filter update, this is called a hidden Markov model filter, but even if you didn't understand, that's not important. What is important is the structure of this update here. That in a classical social learning update, the fact that this guy depends on the prior, pi k minus 1, introduces a structure which looks like this here. So what the structure is something which is pretty interesting. So imagine a filter, a Bayesian update of a Markov chain, which is considered here, where if my belief was in this region here, so if my prior was in this region here, then I have a classical update, just like classical Bayesian. But if my belief was either here or here, then my observation probabilities are non-informative. It's simply 1, 0, 1, 0, meaning it is, regardless of my observation, I do no update. Okay. So here's a case where my observation probabilities depend on my prior. And so the moment I go here, I freeze. There's no update at all because my observation probability is useless. I simply have a predictor which allows my belief to move. So now you have a discontinuity in the Bayesian update because the update when I'm to the right of this line is very different to the update to the left of the line. That means if I look at my dynamic programming equation to model the optimal policy of my decision maker in quickest detection, this is Bellman's dynamic programming equation, this update here is discontinuous, therefore the value function is really weird behavior. And therefore the optimal policy from Bellman's equation, which tells you the optimal policy of the quickest change detector, has this really weird structure. So to summarize, the value function is discontinuous and not concave. Typically, in most of stochastic control, the value function is concave. In this case, it's not. Therefore, the argmin, which determines the stopping region, is non-convex, and you end up with some pretty interesting behavior. Okay. So even in this really simplistic setup, you end up with some highly complex behavior. Okay. So what I've spoken about in part 1, to summarize so far, is I've discussed the Bayesian social learning protocol, and then I've told you how, if you're doing multi-agent quickest change detection, the optimal policy is actually quite non-trivial. It's not simply a threshold policy, it's highly irregular. The optimal stopping region is not convex. And these are pretty unusual results. Okay. I want to say a few more remarks in part 1 and then go on to part 2. So, as I mentioned, social learning and the way humans make decisions is the subject of enormous research, and there are many more sophisticated models. I want to talk about two such models now very briefly. So in the classical social learning model we spoke about thus far, the decision is made by minimizing the conditional expectation of a cost given the information the decision makes. It is known in behavioral economics that humans are not typically utility maximizers or expected utility maximizers. In fact, it's known that humans are risk averse in their decision making. So one thing you can do is replace the expectation operator here by a risk measure R. In simple terms, an expectation operator is an additive operator. Okay, so E of x plus y is EX plus EY. Risk, in its most general sense, is a sub-additive operator. The risk of x plus y is less than equal to risk of x plus risk of y, and that allows you to generalize the whole structure of expectations. So, for example, you can choose this risk to be something called conditional value at risk, which is a very famous risk measure introduced by Rockefeller and Urisev in the early 2000s, widely used in math finance, and you can look at the same structure I spoke about before. And you'll find something interesting. If the decision making is more risk averse, then you would think intuitively, and this is true here, that humans or the decision makers would herd quicker because there is safety in numbers. Okay, if more people herd, it's the safety to herd quicker. And that's what one would see here, that the agents would herd more frequently to a cheaper decision. And it also means that in quickest detection, you have some even more unusual behavior, which I can discuss offline. Okay, so this idea that a human is a risk-averse decision maker is the first interesting generalization. Many of you who are familiar with elementary prospect theory, which was introduced by Daniel Kahneman, of how humans make decisions, know that humans are risk-averse from, I guess, the basic experiment one teaches. If one teaches an undergraduate course in probability, you tell a student that, there are two decisions you can make. Either I give you $10 for free, or I flip an unbiased coin. If it's heads, I give you $100. If it's tails, I give you $0. So your expected value is 50. Most people will just take the $10 and go because they're risk averse to a gain. But most humans are risk seeking for a loss. So if you told a person exactly the opposite, you either give me $10 or I give you the chance of flipping a coin. If it's heads, you give me $100. If it's tails, you give me $0. Most people say, I want to flip the coin. So humans are risk taking when it comes to losses and risk averse when it makes to coming to gains. And that's the typical S curve, which was introduced by Kahneman in prospect theory, where the horizontal axis is the true probability, the vertical axis is subjective probability. And this is kind of well known, but what we're talking about here is a more sophisticated version of that story in terms of risk measures. Okay, the second generalization, which I've looked at, but I'm not going to discuss here in any detail, is a much more sophisticated stochastic control model. So thus far, we've assumed that the decision-making is myopic. I simply have information, I take an expected value and make a decision. Actually, humans make decisions in many ways, but one of the powerful ways of modeling human decision-making is to assume that humans are anticipatory. What that means is that humans freak out about future decisions. So that means when I make a decision now, I really worry about what that decision is going to result to in terms of future decisions. Okay. That unfortunately messes up the mathematics. That makes the problem something called a time inconsistent stochastic control problem, for which dynamic programming doesn't work. Okay, these are called time inconsistent problems. In terms of experimental evidence, these problems are very well studied. There's a simple experiment where, if people are given a choice between having a painful electric shock today or a less painful electric shock tomorrow, most people would rather have the painful electric shock today. You don't want to wait for a full day to freak out about what's going to happen. You want bad news now. You don't want to wait for the next day to have bad news. If you think about it in a stochastic control perspective, what that's doing is that rather than exponentially discounting your cost, you're actually magnifying your cost in the reverse direction, and that does not make it amenable to stochastic dynamic programming. Those problems are called time inconsistent. You have to basically model that as the equilibrium of a game. So it's a much more sophisticated set. So anyway, this problem can be generalized to these anticipatory decision making as well. So you can think of a multi-stage anticipatory decision maker, and that also mimics what a human does. And this can be done in quite a lot of detail. Okay. So that is all I want to say for part one of the talk. I apologize, I don't know what I did there, but okay, that's, if I click done, is that going to get rid of stuff? Or maybe not. It might close things, I'm not going to do that. Okay, we're going to go to the next part of the talk now, which is inverse reinforcement learning. So in part one of the talk, I've given you a quick outline of two things. First, classical Bayesian social learning. Second, a simple hookup of a detector in signal processing, or if you like, elementary stochastic control with a social learner. And we saw some unusual stuff happen. And then I discussed some generalizations of how you make the human decision-making more sophisticated in terms of risk-averse behavior and anticipatory behavior. Now I want to talk about the inverse problem. How do you go from decisions to a utility function? So in part one, in some sense, what we went from was there was a utility function, and we produced a mechanism to construct decisions. How do you do the inverse? So the problem we're trying to solve in inverse reinforcement learning is the following. In a really general sense, from demonstrations of an expert, how do you infer the strategy or plan of the expert? So you're looking at a few decisions, or maybe many decisions. Can you figure out what is the strategy which led to those decisions? And invariably, a strategy is based on optimizing something. So you can ask the question, given decisions, how do I figure out the utility function which generated those decisions? But we want to talk about something even more sophisticated, and that is, the first question is, are those decisions, first of all, consistent with a constrained utility maximizer? So that's a really deep question, right? I mean, it's saying is there intelligence in your data? I have a time series of decisions. Are those decisions consistent with a rational decision maker? In economics, rationality means that the decision maker was optimizing a utility function subject to constraints. So that's the first question. And the second question is, if indeed that's the case, how do you estimate the utility function? So this is a form of inverse social learning, so to speak. We're now looking at decisions of a system, and we're trying to figure out why the decisions were made in that particular way. Actually, my interest in this area came about 6 or 7 years ago when I was approached by a company called Broadband TV, which is a massive company in Vancouver, Canada, and their main kind of selling theme was they were looking at what made YouTube videos go viral. So their business model was this, that you give them a YouTube video with, say, some suggested keywords, thumbnail, which is an image, a title, and a description. And they would modify these meta parameters to maximize how many people watch your YouTube video. So essentially, they were interested in us constructing utility-based models for determining how YouTube users interact and consume content. And you might ask, why is this important? Well, actually, YouTube is a massive economy. I mean, most of you probably know that there are almost 2.7 billion users, almost $30 billion in revenue. And what is really important there is there are more than 30,000 YouTube channels, each with 1 million subscribers, where each of these channels get more than $36,000 per week. So they make more than $1 million a year. Okay, so YouTube is a massive economy where, based on your view count or the number of people who watch your video, there are substantial amounts of money made. And this is simply using AdSense if you look at the number of ads, but then of course there are sponsorships and other things which make the income substantially higher. So you can view YouTube as an economic system. You can also view YouTube as an engineered system. This is where we came in. YouTube is an example of stochastic adaptive control, in the simple sense that you place a video with a title, thumbnail, and descriptors. How do you change the thumbnail or the title or the keywords to increase the view count over time? So you can imagine that you're adaptively changing some of the parameters so that more and more people watch your video. Okay, how do you do that? There are several other interesting questions on YouTube, which we've also looked at, which I won't discuss here, but you can ask the question, when do you place the content? So when do you post a YouTube video? If you are a regular blogger, are there specific times of the week? Do you kind of wait for certain times? And also similar questions happen in interactive advertising. During a YouTube video, when do you optimally advertise? These are all really important questions. I mean, just to give you, this is slightly outside the scope of this talk, but something we found out is that for people who, for example, post videos regularly, say at Thursday at 3 p.m., suppose they purposely didn't do it Thursday at 3 p.m. and waited till the following Friday and posted it, the view count goes dramatically higher. So people can spoof the system deliberately to maximize view content. How do you model the dynamics of such sophisticated systems? They're really important issues. I'm not going to talk about that here. Here I'm going to talk about just IRL related to YouTube. This is something we've looked at quite a lot. So let me say a few things about IRL because it's inverse reinforcement learning, which is also widely used in machine learning. First of all, there's a terminology overload. Different communities call IRL by different things. So of course, in machine learning, it's called IRL. In mathematics, it's called inverse optimization, essentially trying to figure out the cost or the utilities given the optimum. In economics, it's called revealed preferences. And we're going to talk about the revealed preferences idea here because it kind of gives us quite a powerful way of understanding the problem. So in all cases, you have this following setup. You have a reward and a budget. You have a forward optimizer making decisions like in social learning. We're interested in the reverse, the inverse optimization. We want to relate that to the utility. Now, in general, any inverse optimization problem is an ill-posed problem because usually there are many utility functions which can fit a given decision. Okay, so it's by definition an ill-posed problem. And the question is, what can you say about such things? So let's say a bit more about the big picture. Most of you know about reinforcement learning. It's something which is, I think, overly subscribed to. It's a form of implicit adaptive control. Okay, implicit meaning that you're not really trying to estimate the system's parameters. You're directly trying to control the system by looking at the input-output behavior. So the point in reinforcement learning is that by observing the reward, how do you estimate the optimal policy, pi star? Okay. What we're trying to do here is trying to reverse engineer the problem. So IRL, there are many famous papers, actually dating all the way back to Rudy Kalman in the 1960s. So the first paper with inverse L3G was in the 1960s. And you're trying to reverse engineer an MDP. The question is, by observing the optimal policy pi star, how do you estimate the reward? So it's exactly the inverse of the problem we've spoken about. In classical reinforcement learning, you go from reward to policy. Now you're going from policy to reward. Now it turns out, at least in the simple Markov decision process case, which has been studied in these papers, especially when you consider an infinite horizon Markov decision process, it turns out that you can write down your optimal reward as something which satisfies a linear program. Okay? So your optimal reward is something which satisfies a bunch of linear inequalities. So therefore, to reconstruct your reward, if you know A, you simply have to find any feasible solution in this set. So generating an estimate of a reward for a Markov decision process is actually quite easy. And that's done in these papers. It's simply a linear feasibility problem. Right? I reconstruct any reward R hat, which, okay, actually now I've gone back to a nicer form of the, whatever I did there, but this is. I simply construct any R hat which is set valued and solve this problem. So again, I told you it's ill-posed, but any reward that satisfies this linear feasibility condition will do equally well fit the problem. Okay. We want to look at something with a more sophisticated sense in revealed preference. We're not just interested in simply saying, how do I reconstruct the reward? The first question I want to ask is the behavior actually consistent with utility maximization? And then if so, how do you reconstruct the reward? So in the next 3 slides, I want to introduce 3 fairly powerful approaches the first one is actually kind of background information. And if somebody has an economics background, they would probably do it as a first-year graduate student, but it's something I didn't even know about many years ago. So I find it a really pretty interesting result. And it's based on Afriat's theorem, which is a pretty stunning result. The second is much more recent. It's a Bayesian version of that. And this is really inverse social learning. And the third is how do you do adaptive IRL using Langevin dynamics, which is a form of stochastic gradient output. Now, given the time constraints, chances are I will run out of time when I talk about part 3, but certainly parts 1 and 2 will be stuff which I'll discuss in some detail. Okay, so we want to talk about inverse reinforcement learning, a reveal preference approach, and the first question we're going to talk about is a non-parametric way of doing this. So this is Afriat's theorem, which is a pretty interesting result. So the question we're seeking to answer here is the following. I have an agent, and I feed to the agent a probe vector alpha of n, where n denotes time. So I do this for cap n time points. I have a time series of inputs, and I measure the decisions of the agent, which I call beta n, that's the output. And I have these two time series. Okay. Now, we're assuming here that both alpha n and beta n are in Euclidean space. So one way of interpreting this is that alpha n are a vector of prices today. So it could be the price of a toothbrush, a toothpaste, say a loaf of bread. And beta n is the amount the person buys on that day. So maybe the person buys one toothbrush, I don't know, 1.5 toothpaste, whatever. We are assuming the real value. And so this is a response. Okay. The aim of the economist or the analyst is to figure out, is the decision beta n consistent with optimizing a utility function u beta, subject to the linear constraint that alpha times for beta is less than 1. Okay? This 1 is without loss of generality. It can be chosen anything. So the main idea here is that you're trying to detect utility maximization with a linear constraint. So does there exist a utility function u which rationalizes this time series? It's actually a really deep question. I'll give you a time series, and the question is there a utility function which rationalizes the time series, subject to a linear constraint? And if so, can you determine what utility functions you fit the time series? So for those of you with a system ID background, you can view this as system identification of an argmax nonlinearity, so to speak. So here is a stunning result due to Afriat in 1968. It's stunning because it's a necessary and sufficient condition for identifying a utility maximizer. Keep in mind that sufficiency is trivial because if you look at a utility maximizer, of course it's maximizing something. But the fact it's necessary and sufficient is a remarkable result. And this is from microeconomics. It's well known to people in economics, but it's actually something which can be used. And we've used this very profitably in many forms of sensing and other applications of signal processing. So here is a statement. It's actually fairly well known, but let's talk about it. So we have a data set of alpha n and beta n, where alpha n are the probe vectors and beta n are the decisions of the agent. It's a finite time series, so cap n is finite, the number of data points. And then Afriat's theorem tells you that the following 4 statements are equivalent. The first statement is that there exists a utility function. In economics, by definition, a utility function u beta means that it's increasing component-wise with every element of beta. If the utility was flat, it's a useless problem because anything would fit the data. Okay, so that's not interesting. So assume it's a monotone utility. So the first statement is that there exists an increasing utility function beta n, which is argmax of u beta, subject to this linear constraint. The second equivalent condition is that you have these inequalities being feasible. These are linear inequalities in U and lambda. So immediately you can say that a necessary and sufficient condition for there to be intelligence in my data, as meaning constrained utility maximization with a linear constraint, is if a bunch of linear inequalities are feasible, which is actually pretty stunning. It's almost saying that detecting optimization is equivalent to solving optimization, right? Because this is a feasibility problem, and to detect that, I'm using a feasibility. Okay. An equivalent condition is something called GARP, which was developed by Varian. Hal Varian was an economist at Berkeley. Now he's the chief technical officer at Google. And the idea there is that this is a sufficient condition, a necessary and sufficient condition for one as well. It's called the generalized axiom of revealed preferences. And I just want to say a few things about this. This is actually very intuitive. So imagine that when the prices were alpha, remember alpha is a price vector and beta is your response. If your prices were alpha and you bought beta, and if alpha transpose beta was greater than alpha t transpose beta s at some other day, that obviously means that your utility for beta t is greater than utility of beta s. If you're willing to spend more money for beta t compared to beta s, you value beta t higher than beta s. So this implies u of beta t is larger than u of beta s. Similarly, this tells you that u of beta s is larger than u of beta r. So if you're rational and you value beta t more than beta s and beta s more than beta r, then you should value beta t more than beta r. If not, you're not rational, okay? And that's what this condition does. Okay, this is simply a cyclic monotone discrete condition. You can actually write this in graph theoretic terms, and you can demonstrate or check this using something called Warshaw's algorithm in n-cubed operations. But anyway, this is a pretty interesting way of verifying this condition. And the fourth sufficient necessary condition is that you can actually reconstruct a family of utility functions. These are, because it's a min of a bunch of linear guys in beta, these are actually piecewise linear and concave in beta. Okay, so they look something like that. So all these functions equally well rationalize this behavior. And these are piecewise concave linear functions. Okay, so here are some pretty stunning statements from Afriat's theorem. The first point, of course, is that 1 implies 4, the equivalent. And this is actually really interesting. What it tells you is that suppose u beta was a non-concave function. Remember, you're maximizing doing the non-concave stuff. Given a finite amount of data, you can always fit a concave utility function which equally well rationalizes the data. So given a finite amount of data, everything is concave in simple terms, which is actually a pretty interesting result. You cannot refute concavity given a finite amount of data. So that's one of the first important statements. Going from 1 to 2 is actually pretty obvious if you look at the first order necessary conditions. The really interesting parts of this proof are going from statement 3 to statement 1 and statement 2 to statement 1. If these are the non-trivial parts. As I mentioned, this can be checked very easily in order n-cubed operations using Warshaw's algorithm. This is a graph theoretic interpretation. Anyway, so this is Afriat's theorem, a really powerful way of detecting, given beta, if there's a utility function which rationalizes this behavior. It's intensely powerful because you can use this in all kinds of interesting results. And let me just tell you something about this now. First, I want to say a few generalizations of this. So the first question you might ask is, this was a linear constraint. Is that too simplistic? Well, you can generalize it. So Forges and Minelli dealt with the case where you have a general nonlinear constraint. As long as its GN of betas are monotone increasing in beta. Otherwise, you can still detect it, and you still have a necessary and sufficient condition. Okay, so as an engineer, some of the things you might observe in this are the following. I'm listening to a sophisticated radar, which is called a cognitive radar. A cognitive radar is something which optimizes its waveform, the way it looks at different targets in real time. I am the adversary. By looking at the radiation pattern from the radar, the decisions it makes, can I figure out if the radar is a cognitive radar, if it's optimizing utility? Can I figure out what its utility function is? Because once I know this, then I can predict its future behavior. Okay, so that's something which is really important. But of course, in a signal processing context, typically you don't observe the decisions of the radar exactly. You observe them in noise. So now you're in the regime of detection of rationality. You don't exactly have a test, but you're observing rationality in noise. And how do you build a statistical detector to test for rationality? So if you apply Afriat's tests to a data set where beta was observed in noise, if it doesn't satisfy Afriat's theorem, there are two possibilities. Either the agent was not a utility maximizer, or the noise corrupted the data and therefore I'm not getting a utility maximizer. How do I construct a statistical detector which actually detects which one of the two is true? Well, you can do that. You can construct a statistical detector to detect maximization, you can come up with really useful expressions for the type 1 and type 2 error of that detector. And you can do more than that. You can adaptively choose your probe signal to minimize, for example, the type 2 error by holding the type 1 error constant. So let's understand what this means in a really simple way. So suppose imagine that this agent is a bad guy, and you're trying to interview the bad guy to determine if it's good or bad, okay? So alpha n are the questions you're asking the agent, beta n are the responses. Presumably, if it's a bad guy, it's optimizing a utility called a bad guy's utility, and then you detect the person is bad. Now, assuming that the responses are observed in noise, how do you detect if this is a bad guy or not? One way you could do that is for every response of the bad guy, you use that response to adaptively decide what is a new question you're going to ask. And you can do that in a really clever way to minimize the error probability of detecting it's a good guy or a bad guy. Something I haven't spoken about here, which we look at is, of course, if the bad guy is smart and knows that you're trying to detect it's a bad guy or a good guy, it could pretend to be a good guy when it's a bad guy. Well, in that case, really the bad guy is playing a zero-sum game with you. So then the more general question is, how do you detect that this agent is playing a zero-sum game with you? So in other words, given the data set, how do you detect its play from the Nash equilibrium of a game? And that's a much harder question. I'm not going to discuss that here. So anyway, what we've discussed here is something which is purely data-driven. How do you go from data to utility functions? It's exactly the opposite of typically what we do in engineering. In engineering, almost always you postulate the existence of a utility. Usually it's convex, you solve the hell out of it, and you're done. This is dealing with something much deeper. It's saying that given data, is that consistent with utility maximization? And two, can I identify a utility which rationalizes? There are all kinds of generalizations as a result. I'm simply talking about some of the simplest versions of this, and I'm happy to discuss the more fancy versions later. Something we've looked at a lot recently with Lockheed Martin in the United States, the design of radars, is the opposite problem. So given that you have a utility detector, somebody's listening to you and trying to estimate if your radar is a smart radar or not, how do you perturb your radar so as to make your radar act dumb? So in other words, how can a smart sensor purposefully act dumb in order to fool an inverse reinforcement learner? And that's called IRL because it's inverse reinforcement learning, which is a sophisticated form of reinforcement learning. Okay, I'm almost out of time, so I just want to say a few things about Bayesian social learning. So the type of Afriat's theorem I spoke about was non-parametric. Essentially, I have a utility function, an input and an output, and I want to estimate the utility function. Now we can just talk about a Bayesian version of that problem, which is driven by behavioral economics. And this is based on actually the really seminal papers of Kaplan and Dean. Kaplan is a colleague of mine at NYU, and he's an economist, and the papers he's written in 2016 and 2019 are really deep seminal papers in this area, and something which we've kind of worked on. So it's really inverse social learning. So let's start with actually the following idea. So we have a social learner as before, and the social learning is making decisions, and we're trying to figure out what the utility function is. But we're looking at a more fancy social learner who is optimizing its likelihood in real time. So this is called controlled sensing. So imagine you have a radar, for example, in an engineering context, and the radar is deciding how much resources it invests to measure where a target is. If a target is not important, then the radar does not have to invest so much resources. It's wasting its time. So that is a choice of maximizing its observation probabilities. How much attention does it pay? This is actually motivated by behavioral economics. Some of you may know Christopher Sims, who won the Nobel Prize in economics 5 or 6 years ago. And Sims came up with this really remarkable idea of rational inattention. So rational inattention can be explained in this equation fairly straightforwardly. So this is classical social learning. I'm trying to optimize my utility given observations. Now, suppose this observer who was making those decisions, the agent, could choose how much attention it paid in order to get its private observation. Okay. So you can imagine that in economics, you want to give a monetary value to a human attention span, right? So if I pay a lot of attention to read something very carefully, I get a lot of information. I get a very accurate observation. If I spend very little effort, then I get an inaccurate observation. That can be viewed in Bayesian terms. So this is my Bayes update. If my B, the amount of attention span I spend, is very little, then my observation is lousy, and my posterior is roughly my prior. Okay, so the difference between the entropy of the prior and the entropy of the posterior is virtually zero because my observation is useless. I've spent no information. I've spent no attention span looking at it. On the other hand, if I spend a lot of time looking at something very carefully, then my Bayes update after observing is very different to my prior, and this is a huge number. And I'm paying that amount of information for my attention span. So what Sims introduced is essentially the Shannon capacity, this is a mutual information, to model a human attention span. It's a remarkable result. And now you can put this human attention span into your social learning, and this would be a rationally inattentive decision maker. And the question now you can postulate is, given the decisions of this rationally inattentive decision maker, how do I estimate its utility function, its cost function? And the result of Kaplan and Dean is that you can come up with linear inequality constraints which give you the utility function. So this allows you basically to do inverse social learning by looking at the decisions of a really sophisticated decision maker and figure out its utility function. This allows us to analyze YouTube videos on channels and decide under what conditions are multiple YouTube users consistent with a rationally inattentive social learning model. And this is something we've done a lot on. And again, we're running out of time here, but you can show that in many cases, the commenting behavior of users in YouTube is highly consistent with rationally inattentive utility optimization. So much so that you can predict the future commenting behavior with very high accuracy. And this is something we've done in the last 2 years. One of the papers appears in Journal of Machine Learning Research this year in 2013. To do this, we analyzed a massive data set from the company Broadband TV. We used just the basic ideas of rational inattention-based inverse reinforcement learning, and we could actually estimate the utility function in these cases. Okay, I'm rapidly running out of time. I just want to mention one more thing about how you can apply some of these ideas. So another case where you can apply inverse reinforcement learning is in social networks. So something we've been very interested in social networks is the glass ceiling effect. So in real life, the glass ceiling effect is something which keeps specific groups of people from ever rising to positions of importance. It's called the glass ceiling effect. You actually see that also visible in social networks such as Twitter, Instagram, citation graphs, and so on. For example, in citation graphs, it's well studied that women are not cited sufficiently despite the fact many of the papers are of better or equal quality to men. And the question is why? How do you build mathematical models for how there's interaction in citation graphs or in general social networks to show how glass ceiling effects arise? Well, here's a simple simulation one can run. This is called a preferential attachment model. Here is a network where 80% of the nodes in the network are blue, 20% are red, but yet the blue nodes never attain positions of importance. It's very easy to construct such a network. The position of importance here is the power of the node, the number of followers divided by the number of followees. And the blue guys are always stuck here, whereas the red guys are always important, even though they're a minority. It's pretty easy to construct dynamical graphs for which this is true. What we're interested in is the reverse problem, which is essentially a problem which comes from sociology. Why does this happen? Is this consistent with the fact that people attach to other people in a network based on some utility function? And if so, what is that utility function which rationalizes why the glass ceiling effect arises? So this is something we're very interested in, and it's something which is ongoing research. Okay, I'm going to skip the third part of the talk. I'm just going to jump to the summary. So in this talk, we had 2 parts. The first part looked at some really simple behavioral economics models with signal processing. essentially social learning with quickest detection. The second part spoke about inverse reinforcement learning using revealed preferences. We spoke about Afriat's theorem, which is a way of reconstructing a utility given an arbitrary utility with a linear constraint. And then we very briefly spoke about Bayesian utility reconstruction for a rationally inattentive user. I've omitted a lot of stuff here. I'm happy to talk about it offline. In terms of the big picture, at least from an electrical engineering point of view, we have signal processing, we have physical sensors, we have networks of sensors like IoT and so on. You can look at it at a higher level as behavioral economics, which is decision-centric, social senses, which are humans interacting in a social network, and we're really interested in the interface between the two and constructing mathematics for that. And that's roughly what the vision of this talk. If you want further details, my website contains a lot of these papers. Thank you.